Okay, we're at student activity sheet 7 today, and we're looking at a railroad problem. It's very similar to yesterday. We're looking at networks and efficient networks, but it's a weighted graph today. We'll have numbers associated with the edges, and so we'll want to be minimizing the weight in this particular case. We want to minimize the numbers that we're using. All right, so let's dive in. Okay, we're looking at student activity sheet 7, minimal spanning trees. And here's our first problem. A railroad system connecting 5 cities is being planned. The goal is to build this system using the least amount of money while ensuring that each city can be reached by any other city in the system. So you need to be able to get from any city. We have 5 cities here, city A, B, C, and D, and E. You got to get from any city to any other city through the rail system somehow. Based on the distance and terrain, the following chart gives estimates for the cost in hundreds of thousands of dollars to build a railroad between any 2 cities. So create a graph to model the costs contained in the table. So what we're going to have is a weighted graph. Each edge will have some number associated with it. So if I just put down 5 cities here, and it doesn't really matter how you kind of space them out, I'm going to kind of put them in a circle. Then from A to B, I know that's going to cost $100,000. In other words, that's going to cost $1 million to build that piece of railroad. A to C, this would cost $500,000. A to D is $400,000, and A to E is only $200,000. B to C is 7. B to D is 9. B to E is 11. C to D is 5. C to E is 10, and finally D to E is 12. Okay? Restate the railroad problem using the terminology associated with graphs. So the idea here is that we want to state this using vertices, edges, paths, and cycles. So we want to say something like, so let's say construct railroad well, let's say construct a network. Let's change it. Let's construct a network so that all vertices are connected, meaning the cities. And a minimal weight is used for the edges. So we want to minimize the weight of the edges and make sure that everything's connected. Those are the two things that we want to do. So now number 3 says construct 2 different graphs that represent possible railroad networks, calculate the total cost to build each rail system. So get 2 graphs, see how much, what's the weight. We want to minimize that weight as much as possible. Okay, so pause the video, let you do that. What rail system leads to the lower construction cost of your 2? Which one's lower? And do you think it's the lowest? Number 5, how did you arrive at the most efficient rail system? So what was your process that you used? Okay, And then now here's the big part. So number 6, so use your process to try to find an efficient network for these two networks, okay? So remove edges so that everything, we have 5 points, they all need to stay connected in some way. You should be able to get from any point to any other point, but we want to have a minimal weight associated with the edges that are left. Alright? And we shouldn't have any cycles, because if we have a cycle, then that's going to be inefficient. So be sure you remove any cycles. Last question here, number 7. Given any weighted graph like the ones from this activity, does an efficient network of minimal cost always exist? Is there always a minimum? Why or why not? See what you think about that. Okay, I hope you understood that. The next lesson actually goes through a specific algorithm about finding the most efficient network, and we'll look at that tomorrow. Remember that on Thursday we'll start a project. If you can get an empty cereal box, excuse me, if you can get an empty cereal box, it will be helpful. I'll talk to you later.